Now that we've developed all the language for talking about chemical reactions, describing chemical equations, and all this stuff, and starting to look at patterns of reactivity, we want to return to the idea of solutions. When we talked about them previously, we said this was where reactions happen, and so we want to talk about some of the reactions that actually happen in solutions. We previously discussed the motivation for dissolving reactants that you're going to use. The idea being that reactants need to come into contact, right? If two molecules are going to react, they need to touch each other. And that most readily happens in the liquid phase where molecules are freely moving around. So your reactants can come into contact. If they're not, they can come closer together, then come into contact, and then your products can spread apart, go wherever. And so ideally, liquids react the most quickly, but most things that we want to do reactions with are not liquids. So what we do is we dissolve them into a liquid. So we know that we do solution-based chemistry as a major part of chemistry. So one of the questions we define specifically water as aqueous. We've talked about aqueous phases. Why use water as our solvent of choice? And there's a couple key factors. One is utility. Water dissolves a lot of things. Not everything does necessarily dissolve in a given solvent, and water can get most biologically and chemically relevant things. Another liquid would be like octane, for example, so gasoline, a primary component of gasoline. Liquids like gasoline do have their utility for dissolving things. There are some biologically and chemically relevant compounds that do dissolve in gasoline. So octane is used some in labs, or compounds similar to octane, but it has less widespread utility. Bromine is another liquid. It just doesn't dissolve a lot of things. So it's not very useful in that regard. If you could get something to dissolve in bromine, it would have that same properties of being dissolved, floating around, colliding things. It's just hard to get things to dissolve. Another big aspect is reactivity. Water is very unreactive, so water itself doesn't do a lot of chemistry. And if you think about forming solutions, you're just trying to get reactants to dissolve and do their chemistry. You don't want to really worry about what the solvent is doing. What you really don't want to worry about is, say, the solvent reacting with your reactants, doing some other reaction. Octane is highly flammable, so it's not necessarily reactive with whatever you dissolve in it, but you have to be really careful around, say, flames or anything like that. Bromine reacts with whatever you dissolve in it, probably. Bromine is an extremely reactive liquid. And so if you, say, had some reactants that you want to react, if you were to get them to dissolve in bromine, they would just start reacting with all the bromine that's present. The final big issue is price. Water comes from the public water system. So we have sinks we can get it out of. That's really nice, really advantageous. It's one of the most widely available liquids. We do want to potentially use, deionized water in the lab, but we can still make that ourselves from publicly available water. Gasoline, you can still pretty easily get gasoline. You have to buy it from, say, a gas company. It is more expensive than water, but still you can get large quantities of it pretty easily. It is slightly difficult to transport because it is so flammable, but certainly is possible. Bromine, I highly doubt you have any idea how to buy bromine. That's because you have to get it from specialty chemical companies. They don't just ship liquid bromine to anybody. So it is a much more difficult to obtain, and as a result, it's also quite a bit more expensive. So water is very useful. It's very unreactive, which is good for this purpose, and it's really cheap. As far as liquids go, it is one of the cheapest liquids that exists. And so it's really nice to have all of these basically checks every single box you would want, and it's all in one nice liquid. So that's why we use water, and we do a ton of aqueous chemistry. That's why your body is full of water, and your body is doing a ton of aqueous chemistry. So what happens when we dissolve things? We know that the molecules separate out, and the picture we've kind of talked about previously is true for covalent compounds. If you have a covalent compound, for example, sugar. Sugar dissolves in water, and it goes from being solid to being aqueous. And so what that means is if you have a solid, say this region, the sugar molecules would all be packed in together. And when they go to dissolve, they then move apart, being independent of each other, and they can move around freely. But importantly, you will note that the molecules stay exactly the same. If you look at a snapshot of, say, one of these molecules that's in the solid phase, it's just kind of a rotated version as the molecule that's dissolved. You haven't changed the molecular structure, you haven't broken any bonds. So when covalent compounds dissolve, they dissolve as molecules, right? They start as molecules, they're just kind of placed together in a solid, and so when they dissolve, they just fall apart and are floating around freely in solution. Ionic compounds, on the other hand, actually experience bond breakage. When ionic compounds dissolve, they separate into the ions. So if you had sodium chloride solid, this is sodium and chloride ions close together, right? The solid crystal right here, you have both ions together. When they dissolve into two separate species. So you would have your anion chlorides floating around, and you would have your cation sodiums floating around. They float around independent of each other. You'll note it's still neutral overall because the positive and the negative both separate out and dissolve. But when we actually have aqueous ionic solutions, the ions are actually separate. It should be noted, even though what really happens is the ions are separate, it is not uncommon to see a description of NaCl aqueous, right? We oftentimes would put AQ after the name of the compound just to denote that it is dissolved. It is going to be implied that those ions have separated out and are interacting independently of each other, moving around independently of each other, just kind of floating around in the water. One of the aspects of, because of this property, when we dissolve ionic compounds, we oftentimes call them salts. So salt is a reference in the chemical context to just really any ionic compound, but especially ionic compounds in the context of being dissolved in water. When they're dissolved in water, they have the separate ions. We call those salts, really within that context. And you'll see it applied to anything that salt means any ionic compound. That's why sodium chloride here is oftentimes called table salt in a chemical context. So with that in mind, we would like to look at some examples where I have some solids. I'm going to dissolve them in water, and I would like to complete each of these chemical equations. So let's take a look at how that works. So we have our compounds that we're looking to dissolve in water. And so we want to complete each of these chemical equations. So really what we just need are going to be products, right? We're given the reactants. We're told we're dissolving them in water. So we want to see what's going on. Predict those products. And whenever we are looking at dissolving something, really the question we're going to ask is this thing ionic or covalent? Because just like naming, just like all the other properties, how things dissolve is going to depend on whether or not it's an ionic compound or a covalent compound. Okay? And so if we have KBr, that'd be potassium bromide, we want to know whether or not it's ionic or covalent. We can look and see that potassium, way over here on the periodic table, is a metal. Okay, so our dividing line's over here, way past it. Potassium is a metal. And so since it is ionic, we know that ionic compounds separate out into their ions when they dissolve. So I have the K and I have the Br. I know that they're going to turn into independent K aqueous plus Br aqueous. They're going to be aqueous, which means that they're actually dissolved in that solution. Okay? And so that looks great so far, but we want to not forget our last step, and that is we need charges. These are ions. When they dissolve, they need to still show those ions, the charge that they have, right? And KBr, we can't necessarily predict the charge just from the formula. What we can do is return to our periodic table. K is in column 1A, so it is going to be positive. Bromine is over here. column 7A. This would be my 0 column, -1. So Br minus. So potassium bromide becomes a potassium cation that's floating around by itself in solution, and a bromide anion that's also floating around by itself in solution. Okay, so far so good. Let's take a look at Na2S, sodium sulfide. Sodium is right below on the periodic table, or right above, sorry, potassium on the periodic table. So that is also going to be ionic. So this is going to break right there. So we know we're going to have Na, aqueous, and sulfur, aqueous. So we separate out our ions. We do want to be careful not to forget those charges. Sodium was in column 1A, so it's plus. Sulfur is in column 6A, so 0, -1, -2 for sulfur. Right, it's a 2 minus. Okay, so that's good. We got our sodium plus sulfur, separate ions floating around. But you will notice that this is not balanced. We had, I kind of wrote over it, there's a 2 beneath that sodium. So we had 2 sodium atoms here, we need 2 sodium atoms right here, and that goes in front. So we want to be careful. We do not want to write, we should not be writing, I'll do a different color to show that it's wrong. It should not be Na2 2+ aqueous. That is no good. We don't want that. Because if we think about what this means, when we have, this would imply that those 2 atoms are attached together, and that's like some sort of polyatomic cation that's floating around. But instead, this Na2S really means you have Na+, you have an S2-, and you have Na+, right? Those are all of your ions together in the ionic solid. And then what happens is when you dissolve, all of them break apart, right? These water molecules come in and break it all apart, and you lead to them floating around separately. So this is 2 sodium atoms, 2 sodium cations together, and held together in this compound, and then when it dissolves, they just float apart from each other. They're now totally independent when they are dissolved. So the 2 goes out front, because that implies there are 2 different sodium cations. If the 2 is a subscript, you are implying that those atoms are linked together in like a molecule or some sort of compound, something that is a single substance where they would be floating around together. But instead, they move independently of each other. Got a little low on that one. So Na2S becomes 2 Na+ and S2-. NH4Cl is ammonium chloride, and we want to be careful on that. When we see nitrogen, we may want to think, hey, that's a non-metal, right? But when we see NH4, that's a polyatomic cation. NH4Cl is in fact ionic. Okay, so we separate out into ions. We keep NH4, and that's a plus. We know that's ammonium. We can't use the periodic table. We just need to know that or look it up. When we see that, we want to recognize NH4 is ammonium, NH4 plus, and then the other one is the Cl, and that is minus. Chloride is a halogen, or chlorine's a halogen, just like bromine, so they have the same charge. They're in that column 7A. But you'll note the NH4 stays together. We do not separate the atoms of a polyatomic ion. So those NH4, that all stays together. We keep them all linked up because that is a molecule, right? This was not a single molecule. That was 2 independent atoms that should be floating around away from each other. This is 1 molecule. It should be held together. Those atoms are packed together. When you dissolve an ionic compound, you only break the ionic bonds. You do not break the covalent bonds holding this polyatomic ion together.
Finally, CH3Cl. We have a solid, we're dissolving it in water. Start with carbon, that's a nonmetal. Hydrogen also a nonmetal. Chlorine also a nonmetal. CH3 isn't any sort of fancy polyatomic. This is covalent. And so because it's covalent, we don't separate out. It just becomes aqueous. We do not break covalent bonds. The molecules just become separated. You don't change the form. You just add AQ. All you do is change the phase because that's all you have done when you dissolve it, is you've just changed the phase. Because it's covalent. For the ionics, those are a bit more. You're breaking those ionic bonds, you're separating out the ions. So we separate them out K plus, Br minus. We want to not forget, we want to separate out any sort of monoatomic ions, need to be fully separated. And when we have the polyatomics, they stay together. Covalent compounds, the entire thing stays together.
This different behavior between the dissolving of ionic and covalent compounds leads to two different types of solutions. We have electrolytes and non-electrolyte solutions. And electrolyte solutions is anything that contains ions. When you dissolve a salt into water, you create these independent ions that are floating around, say plus and minus, right? Floating around independently of each other, moving around, charged particles. That allows for the solution to conduct electricity. Pure water actually is a pretty poor conductor of electricity. You may think like, if you're out at swimming, you want to get out of the water if there's a lightning storm. That's because you're not swimming in pure water. You're swimming in water with a fair amount of salt in it. Even if it's, let's say pool water, there's still a decent amount of salt in there. And so that's why it conducts electricity. Pure water, like say the deionized water that we use in lab when we're doing kind of fancy stuff, that is a poor conductor of electricity. You won't really get a lot of flow through that. But any water with salt in it, which is pretty hard, you have to try to deionize water. It tends to have a lot of ions floating around in it. That causes the conduction of electricity. If you dissolve covalent compounds into water, that is called a non-electrolyte solution. So that'd be what we have over here. Say sugar, when you dissolve sugar into water, it doesn't separate out into different ions. It's not going to conduct electricity. So if you started with water and pure water and you added sugar, it won't change the conductivity. It won't change those properties. It still is not going to conduct electricity.